So anyway, catoids, they are just little gadgets that allow us to streamline somehow the development of models for logics of programs and algebras of programs. And this is what I want to talk about today. So maybe the computer doesn't like me. Voilà. So, okay. So, I mean, part of my work is on algebras of programs, which are basically algebras in which you can model imperative programs and then analyze them and verify them and stuff like that. And typically these are semi-rings, so rings without a minus, or Kleene algebras, which are related to these semi-rings, as you can see, quantales, which are slightly more rich structures, and then relational algebras, algebras of binary relations. And I've developed variants of such algebras, and in particular been involved in the development of so-called modal Kleene algebras and concurrent Kleene algebras. And we have studied models of these algebras, mainly models that are interesting for computing and for giving semantics to programs, and also properties such as completeness properties of such algebras relative to models. Free algebras in this context, decidability properties, and so on. And then last but not least, in order to really verify programs with these algebras, we have formalized them and their models with proof assistance. And in my case, notably the Isabel proof assistant, which is like a specification environment in which you can formalize mathematics and execute mathematical proofs. And then we have built little verification tools based on them. But when I was formalizing these models, I often felt like a musician who was playing variations on some theme without knowing what the theme actually was. I had the impression that I was repeating constructions, which were all very, very similar without understanding what the kind of general construction behind this. And I think catoids allow us to explain what it is. And this is basically the story that I want to tell you today. So let's start with Kleene algebra. So Kleene algebra is named after Kleene, the famous logician and recursion theorist. And in the early 50s, in 51, he wrote a paper on the representation of events in nerve nets and finite automata, which set out basically this kind of holy trinity of automata theory as we know it today. Regular expressions, regular languages, and automata that accept them. Where you can see essentially the automata as programming devices. The languages represent the behavior of the computational gadget, so to say. And the regular expressions, they are algebraic expressions that denote these regular languages. And there's also a logical side to it that I do not want to mention here today. So for those of you who have never seen this before, so regular expressions are built by the following grammar. 0 and 1 are regular expressions. The letters A in a finite alphabet in a set sigma are regular expressions, and then sums and products of two regular expressions are regular expressions, and the star of a regular expression is a regular expression. Regular expressions are intended to denote languages. Languages are just sets of finite words, so they are built in the free monoid over the alphabet. And that includes also the empty word. And so, for example, there's an interpretation map from regular expressions to sets, well, essentially into languages that define regular expressions. And it maps the empty, the regular expression 0 to the empty language, 1 to the language that contains only the singleton set. Then also every element of the alphabet to a singleton language. The sum of two regular expressions to the union of the resulting languages, the product to a language product, which for algebra is essentially a complex product, and then the star to something that mathematicians normally would not consider. So then Kleene algebra, in his original paper, he wrote down equations or identities between regular expressions. And they were based basically on the fact that they denote the same language. So, I mean, there's no one-to-one correspondence between regular expressions and languages. And then Kleene did not ask this question, as at least I could not find a precise question in his paper, but somehow the plan was obvious. You know, it was basically to find an algebra of regular expressions, a regular algebra or a Kleene algebra that axiomatizes precisely this congruence. So two regular expressions are equivalent if and only if they denote the same regular language. So you want to find an algebra which has the same signature as the regular expressions, and then prove in particular soundness and completeness with respect to regular expressions, so that you can prove that two regular expressions are the same from using the axioms of Kleene algebra, if and only if their denotations are the same. So you could also say that what you are essentially doing is you're trying to give an algebra such that the regular languages form the free algebras in the variety, in the sense of universal algebra, so in the sense of the equational theory. So that is what Kleene algebra is about. And people started to make progress over the years, but nothing significant happened really for 20 years until John Conway entered the area. I mean, people told me it was because he wanted to learn about the algebraic side of automative theory. And in order to do that, he wrote a book about it. And after that left and never came back, right? So probably he found it boring, I do not know. But what Conway did in this book was not really giving answers to all these questions, but he was basically giving conjectures and crazy ideas, if you want. He said, oh, I think this is an axiom system, and I think you could do the proof like that. And, you know, he sketched it on 2 pages. And then this could also be an axiom system. And why don't you try this technique? And then after that, it took another 20 years for people to work out these proofs. The first proofs along the line from Conway was given by a person here from Paris, Daniel Krog, and it was a 150 theoretical computer science paper working out the 2-page sketch by Conway. And then there was another proof by Dexter Cozen a couple of years later, which is short and beautiful, but again, based very much on ideas that came from Conway. So that's the story. And then what ultimately became known as a Kleene algebra is the following set of equations. So in blue, you just have a semi-ring, a ring without minus. And then in violet, or whatever this color is called in English, you have other equations that are a little bit strange for many people. So for example, addition is idempotent, but this comes from the fact that obviously the denotation are languages, and the plus is the union of language, and the union of sets is idempotent. So that should not be surprising. Another thing that some mathematicians might not like is that the multiplication is not commutative, but this we know from matrix semi-rings, so maybe we can live with that. And again, we can explain it, of course, based on the languages. And then there are axioms for the star, which was another regular expression. Well, I mean, these essentially model the star, which is some sort of finite iteration of languages, as a least fixed point. But I do not want to discuss them in detail because they don't matter for my talk, and later on I will make the star even disappear completely. Anyway, and then on that axiomatization, based on that axiomatization, Dexter Cozen in the early 90s gave a completeness proof, which is basically the right to left direction. And I mean, in my personal taste, it's a beautiful proof and one of the pearls of theoretical computer science. So if you want to prove soundness, which means that everything that you can derive in the Kleene algebra also holds in the language model, you essentially just construct this language model. So that's the first model that we have. So sets of words, languages under union, language product, which is essentially just the complex product, the empty set, the language that contains only the empty word, and the star of languages, which is just defined as a union of powers. The powers can be defined recursively, but essentially what you're doing is that you're taking all the languages in the set and compose them iteratively with each other. I mean, it's a simple construction if you think about it. And and you can show that these form Kleene algebras. But in fact, you know, you could do this construction for an arbitrary monoid. It doesn't have to be the 3 monoid sigma star, and you would still get a Kleene algebra out of it. And then, you know, once you have this model, it's easy to see that the regular languages, which are generated by this morphism that I showed you before, they are actually just subalgebras, and that is something. So languages can be generalized to what people call weighted languages, and weighted languages are used a lot in computing in fields such as speech recognition and natural language processing. So now weighted languages are functions that map from the free monoid into, in this case, a Kleene algebra K. So normally people would use a semi-ring, and the semi-ring gives you weights. Right? And now on the algebra of weights, you can also define a Kleene algebra. And the operations are as follows. So the sum, the weight of the sum of the weight of two words is basically computed as the weight of the sum. The empty weighted language maps every word to the weight 0. Then the product of two weighted language is computed as a convolution. So you basically split your word in all prefix suffix pairs, compute the weight of the prefix with f, the weight of the suffix with g, multiply them in the Kleene algebra, and then take the sum. And you can actually use a sum because there are only finitely many prefix suffix pairs for each word, because the words are finite, right? So you can really represent that in the signature of the Kleene algebra. Then you have an identity map, which is basically like a delta function. So it gives you value 1 if the word is the empty word, and value 0 otherwise. And then you can give a complicated recursive definition for the star that I do not want to discuss. Now, standard languages are just languages that take weights in the Kleene algebra 2, 0, 1, the Kleene algebra of the booleans, because then this weighted language just becomes a characteristic function for sets.
What is x in the last formula? X equal
Yeah, x is equal to w. Thank you very much. Okay, so now in the completeness proof, Dexter-Cosen formalizes matrix Kleene algebras, and something that is hidden as a secret, is kept secret to computer science students, is that automata, which are these little graphs, are actually matrices, right? So, but as graphs, it's very obvious that they have adjacency matrices, and what you put as coefficients is just the labels that you have. So, for example, here you see that you have a plus b, which means that you have a non-deterministic choice between an a and b, and so on and so forth. And the two vectors that I have, they just encode the initial and the final state. So 0 is the initial state, so that's why it's up there. x2 is the final state, that's why it's down there. And then you can show that Kleene algebra is closed under matrix formation. Yeah? What you do is you just use the normal matrix operations as we know from secondary school. But if you stare at these operations, you see that, again, they are basically the same things that I showed you on the previous slide. Right? So, for example, the matrix multiplication is again a convolution operation. So the only thing that has really changed, the weights are the same, the weight algebra is the same. The only thing that has changed is the coefficient algebra, right? So before I had the free monoid. Here now I have some obscure algebra on all that pair that I somehow need to take into account. Okay, the star is again somewhat tricky. You can again compute the star in a recursive fashion, but again, the star does not matter so much in my pair. I wanted to show it to you, but I did not want to explain it. I can do it after one glass of champagne if you wish. So relations, a very important model for computation, because imperative programs have relations as a standard semantics. You can see them as discrete systems if you wish, but relations are just Boolean valued matrices, right? So you just restrict the matrix algebra that we have seen so far for the Booleans, and then we automatically get relations. And then, we have again a Kleene algebra that is union of relations, then relational product here as the product, the empty relation, diagonal relation, and the star is essentially a reflexive transitive closure operation. So if I can go with R star from A to B, then I can go in K steps with R from A to B for some K. That's basically what it says. But now we have a little problem, because if you want to write it nicely as a convolution, we can't do that. Yeah, because now here I'm actually summing. I'm supposed to take the supremum over an infinite set. I cannot bound it. Relations can be infinite, so they are infinite matrices if you wish. So we cannot express this anymore in our Kleene algebra. So what do? we consider a Kleene algebra in which we have infinite suprema, arbitrary suprema, and arbitrary infima. Because if we have arbitrary suprema, we get a complete semilattice. Every complete semilattice is automatically a lattice. So Conway called Kleene algebras that are defined over a complete lattice, complete Kleene algebras. But today, a more popular name for them is wrong direction, is quantale, right? Where quantale is essentially a complete lattice, which is at the same time a monoid, such that the multiplication of the monoid preserves all subs in both arms. That's the definition. So there are interesting examples of quantales that I can use as weight algebras. So for example, the so-called Lavier quantale, which gives us generalized metric spaces, and it is very popular in fuzzy algebras, and you can model T-norms with it and stuff like that. Or you can use the isomorphic quantale defined over the unit interval that you can use, for example, for modeling probabilities. And so you can have Kleene algebras, or all these models, you know, you can have weights in that are probabilities. Now doing this, we can now construct indeed Q-valued relations, and there are entire books written about this subject, for example, by Tholen and Hoffman. Or you can have convolution quantales over arbitrary monoids. You can also not keep your splittings finite. Monoids are nice, but here again, we do not quite know what the underlying coefficient algebra should be. So I give you another example, which makes it maybe clearer. It's also something that people have looked at in this kind of algebra of program community. Sometimes you want to have more precise information about executions of programs than relations, which just give you input-output relations. You want to know precisely the traces of the program. This is in particular important for concurrent programs. So you want to trace each state they visit and each action they perform. So what you want to have is basically path objects. So abstractly, and that is no secret for people who know, for example, a bit of representation theory, or know MacLean's book about capital theory. So you model a directed graph simply as a pair of source and target maps that map edges to vertices. And then you define paths over them as these alternating sequences, like indicated here. And you can extend the notion of source and target in a natural way to paths, to the beginnings and the ends, and write their types, you know, so the paths are now something like arrows in a category, and you can define a product of paths where you just glue them on their ends, like indicated in this diagram. And then again, you can define a complex product on it. So now you have sets of parts that you compose whenever they match on their ends. You can have an identity in the setting, which is given by the parts of length 0, which are just vertices, sets of vertices seen as sequences. And that gives you also a Kleene algebra or quantale, and you can add weights to them, and you can do all the constructions that we have seen before. But now what we have actually built here is the free category that is generated by the directed graph. So we could ask the question, can we lift any category to such a convolution Kleene algebra or quantale? And again, the answer is yes. And people know these structures. They are known as category quantales. And they are generalizations of, for example, the monoid algebras or the group algebras that are used in representation theory, but with strange weight algebras, because they are not rings or something like that. They are really quantales. Okay, we can do all these constructions. So now the idea is, should we take basically the categories and build everything over, let's say, domain algebras for our functions that are categories. And in particular, what would be nice to use as a model here are so-called single set categories, which you see, for example, in chapter 12 of MacLean's book. I mean, they're not very popular. Peter Freit has written 2 books where he uses single set categories. One book about abelian categories, another on categories and allegories. But apart from that, they are not very much used. So a single set category, the idea is that you just consider the arrows of the category, and then you use the source and the target maps to identify which are the identity arrows in your system. But then, of course, there's a one-to-one correspondence between identity arrows and objects. So you can forget about objects as well and model everything as such a, let's say, partial monoid. And in particular, you can see that X is an identity as X is a fixed point of S of the source map or a fixed point of. So that might be a good idea, but again, we have a model, an example that is computationally interesting that does not really fit into the scheme. And this is shuffle languages. So in language theory, we have seen this kind of language product, but the shuffle of two languages basically takes two words and interleaves them in all possible ways while keeping the word order of the individual words intact. And that is a so-called multi-operation. Right? It maps basically two words to a set of shuffles that we get, and that does not really fit within the scheme of a category on the nose. So we can extend it again, like before, to the language level. We have to flatten here because otherwise we are one-dimension app in the power set of the power set. And we can show that this is a shuffle quantale, and we can build convolution algebras in the same way we have done it before, with the only difference that now we take an element relation instead of an identity. So, and that is basically the level of generality that we would like to have. So a little bit more than categories, so to say. And there are other reasons why we want to have that will become apparent later. And this is basically the definition of a catoid. So a catoid is basically just like a category, but we have a multi-operation instead of the standard composition operation for categories. And we are supposed to satisfy three axioms. So the first axiom is really difficult to understand, and it would take me more than 30 seconds to explain. But instead of doing that, I say we just take our multi-operation that we have lifted to the power set. Right? Like again, like a complex product that we have to flatten in order to give it the right height. And then this first axiom just becomes associativity. And associativity means here I have my multi-operation on words, so it gives me a set. This is the lifted operation. And here I was too lazy to write brackets around braces around the X and here around the Z. Right? So essentially the first axiom is associativity, and this is what some people call multi-semigroups. In some contexts, they're also known as hyper-semigroups, for example, in the work of Alan Kant. And then the next axiom that we have, it tells us just that whenever the composition is non-zero, which means essentially the composition is defined, it returns something different than the empty set, then the target of X must equal the source of Y. So here I'm using the opposite direction of composition to categories, right? It's basically in the direction of the diagrams. And then here these two just tell me that the source of X is the left unit of X, and the target of X is the right unit of X. So it's basically just that. Okay, so we generalize categories, so we should also be able to generalize morphisms. And now morphisms, they have been well studied, for example, in partial algebras or partial semigroups. They are these kind of inclusions, serve the source and the target maps. And there's also a notion of bounded morphism. So the morphism basically goes from X to Y. The bounded morphism in some sense goes back from Y to X. And this is very well known in modal logic. So there it is sometimes called p-morphism, or computer scientists like to call it functional bisimulations. That's basically what you get from these morphisms. Then we have two definitions. We say a catoid is functional if it either maps to the empty set or to a singleton set. And we call it local if it satisfies the other direction of the defining condition. So here we have now the target of X equals the source of Y if and only if the composition of X and Y is non-zero, and that is precisely the composition pattern that we have in categories. So we see that every single set category is a local function, a catoid, and in fact we can extend this to an equivalence of categories if we consider also the morphisms given. And like in the example of Kleene, the source and the target maps, the fixed points that we have here, these fixed point sets, they determine the precisely the identity elements that we have in this setting. So it's a little bit more, a catoid is a little bit more general than a category. All structures that we have seen so far are catoids. Relations are now constructed easily over the pair groupoid, which is an instance of a catoid. The shuffle languages form the shuffle catoid. Here the operation, the parallel composition is even a total operation, and this kind of source target structure is trivial because it maps everything to the empty word. But there are many other interesting examples from computing that I think justify this generalization. Okay, now we know what our sources are, basically, or our domains are. These should be catoids, and then we map into quantales. And now let me explain the construction. And the construction of all these algebras is inspired by the so-called Johnson and Tarski duality, which is an extension of Stone duality for Boolean algebras. And there's a topological side and an algebraic side to it. And I will only speak about the algebraic side, which is the easier side, right? So Johnson and Tarski have discovered in the 1950s that there's a duality between Boolean algebras with operators, which are Boolean algebras on which you can have n-ary functions, endo-functions that map back into the algebra on the one hand, and they call them n-ary modality. And on the other hand, relational structures, which are built from n-ary relations. So whenever you have an n-ary operator over the Boolean algebra, you have an n+1-ary relation. So we have seen examples yesterday. So there we had unary modality, the knowledge operators, and we had binary relations, which gave us a quick gift. But it works in all dimensions. So what we do here is one step up from yesterday. So we consider our convolutions, for example, as a binary modality on the quantale, and then below on our catoid, we consider our multiplication as a ternary relation, which is easy to be arranged by a little bit of currying and uncurrying, as computer scientists would say. So you can write this as x times x times x to 2, which is basically a ternary relation. So what's the idea of this construction? So here we need only, I mean, they considered it for arbitrary Boolean algebras, then in particular for atomic Boolean algebras. And then here we only need power set Boolean algebras or something like that. Right, so the idea is that in this duality, and you have on the right hand side your power set structure, you can find your ternary relation within the atom structure, which is given by the singleton sets. Right? So you say that x, you have the ternary relation x is in y composed with z, if and only if the right hand side. Yes, that's right. The right hand side holds. So the atoms in the power set structure define a relational structure. And on the other hand, whenever we have a relational structure, we can define the power set structure just by giving given the complex product and flattening it because of the type of our operation. And then Johnson and Tarski shown that we have dualities. So the double dual of a Q is isomorphic to Q in the sense that when you start with your power set structure, retrieve the relational information in it, and then build up again a power set algebra from it. It's isomorphic to Q. On the other hand, if you have a relational structure, build the power set structure from it, look inside and retrieve your relation, it will be isomorphic to X. And you can generalize that to a proper duality, where you have on the quantale sub and multiplication and unit preserving maps, and on the catoid you take precisely the bounded morphisms that we have seen 2 slides ago. So what is more interesting for us than this duality proper is that every duality in modal logic gives rise to modal correspondences. So you can basically translate identities between X and Q. And this is what we are going to use. So we get these kind of Eiffel towers. If we generalize from power set structures to convolution algebras, there we get 2 out of 3 theorems. If you have structure in X and in Q, it translates to structure in the convolution algebra. If you have structure in QX and Q, it translates back here, and so on and so forth. And in the convolution algebra, so the modality that we have, the binary modality is given by convolution. The identity is like a delta function. So the identity at point X is 1 if X is in the set of units, and 0 otherwise, and the rest is basically lifted or is extended pointwise. Okay, the basic correspondences that we get is that if X is a catoid and Q a quantale, then the convolution algebra is a quantale. And then the other remaining duality, I will only talk about the second one, the third one is not so interesting. But the second one would say if the convolution algebra is a quantile and the weight quantile is supported, which essentially just means that I have 3 or 4 elements that allow me to do the construction, then X will be a catoid. And of course, we get Kleene algebras instead of quantales if you have these kind of finite decomposition properties like we had them for words. So here are two examples, and I don't want to discuss the proof. I just want to point at 2 or 3 places. So it shows basically that we get, when we get associativity at the level of convolution, of the convolution algebra. And after some, in the first step, just unfolding definitions, you can see then from the second to the third step that here we use associativity in the catoid, and here we use associativity in the weight algebras. So you see really how associativity in 2 of the algebras gives us associativity in the third one. And here we see how associativity in the convolution algebra gives us associativity in the catoid. And these delta functions are really what you think they are. So such a delta function gives me weight 1 in the quantile if u is equal to the value x that I put at 0 other x. Good. So now I want to discuss 3 applications. So 2 standalone application, and then the third one which combines the 2. So the first one is catoids and modal quantales. So modal quantales are basically algebras that we have built over over quantales, I should say, and they allow us to verify programs. So the idea here is that I take a quantile, and I think in particular of the quantile of binary relations. So the elements of the quantile are binary relations, and you axiomatize a domain function over it. It's the domain of a relation. If the relation is a program, the domain of a relation gives me the set of all states from which the relation can execute. That's basically what I've written down here. And the codomain gives me the set of all states in which the program can execute. That's here. And what the particular axioms are does not really matter. I mean, they all have their meaning. They all make sense. When I have a domain quantile, I can take a codomain quantile by just taking the opposite of the quantile, flipping the order of multiplication, and then taking domain instead of codomain. And then a modal quantile is where I have a domain and a codomain operation, and then I have this compatibility condition between domain and codomain. Yeah. And you can define, I mean, that's a little bit of an aside. I mean, you can define modal operators on these quantiles, modal diamond operators, modal box operators, where basically the modal diamond here gives me the set of all states from which, if I execute my program X, I may end up in states that satisfy P. And the box operator gives me the set of all states from which, when I execute my program X, I must end up in states where I satisfy P. So, you know, you can then use that in order to specify, for example, correctness properties of programs. And what you get, I mean, just to put this in context, is what people call dynamic logics. It's basically algebraic variants of dynamic logics. Or some people call it predicate transformer algebras. It's related to so-called weakest liberal preconditions or weakest preconditions. Or again, you know, it's just Boolean algebras. As I said, we can use it to verify programs. And in particular, we use this kind of relational semantics in order to do that. In this context, we interpret the plus operation as a non-deterministic choice of programs. The multiplication is a sequential composition, and the star is a finite iteration. And I think we saw it yesterday morning on Uli's first slide or something like that. And then in a Boolean quantile, we can also give semantics to if then else and while loops. And then we can write these kind of specification statements about programs in this modal language and implement it on a computer and you know, verify that Euclidean division is correct or whatever. Okay, but coming back to what I wanted to say, there's a very strong correspondence between catoids and these modal algebras. And every local catoid and the modal value quantile gives rise to modal quantile on the convolution algebra. The definition of the domain is slightly complicated, and I only want to show you the power set case. So in the power set case, if X is a local catoid, then the power set algebra, the complex algebra, is a modal quantile. And in particular, the domain and the codomain operations are just images of the source and the target map in the catoid. And the multiplication that I have is just the lifting of the multi-operation that I had on catoids. And in particular, again, you see how operations lift in a one-to-one fashion. So this is what we call the locality law in the domain algebra. In order to prove it, I'm full definition. And here I use essentially just the locality corresponding locality law on the catoid that I can derive. And for the other direction, if I want to prove the locality law in the catoid from the law on the algebra, well, I know that basically the domain operation is just the image of this, but I apply here the image to a singleton set, right? And then again, I use locality in my domain algebra, and I get my result very easily. So to sum up, what does it give us, right? It tells us if you want to build a modal convolution quantale or power set quantale, you should look for whether your underlying structure is a catoid. And if you have found your catoid, the rest of the lifting is generic. In particular, you can do that for any category. So every category gives rise to such a modal algebra. And you can see that the locality axiom that I showed you on the previous slides captures precisely the composition pattern of categories at the power set level. And you can see that, for example, the domain axiom, one of the domain axioms that we have here is precisely, so to say, a lifting of the left unit axiom for the of the catoids. Okay, so now I want to start with my second example, and I want to say something about concurrent Kleene algebra, concurrent quantales, and how catoids play a role there. So we know that word concatenation, we can show that word concatenation that we have seen interacts with the shuffle of words that I've shown you before by an interchange law, as we know it from higher categories. You can prove that. The proof is surprisingly tricky. I think it requires 3 nested inductions if you use the recursive definition. But anyway, you can prove that. And then you can quite easily lift it to an interchange law at the power set level. So that motivates a more general definition. So you define an interchange catoid as basically 2 catoid structures in parallel that interact by such an interchange law. And then you duplicate the same kind of definition at the level of quantales. So you take 2 quantales with an interchange law between their compositions, and you call that an interchange quantale. And then you get the standard Eiffel Tower, right? So you can get 2 out of 3 laws. And all you need to check at that level, because we know already these correspondences for the quantales, all we need to check is really the correspondences between the interchange law. That's it. So what can we do with it? First of all, in so-called interleaving concurrency, where we shuffle the objects that we have, we can construct weighted shuffle languages with interchange laws. So the shuffle operation is commutative, but we also have a 2 out of 3 correspondence for that one. Yeah, and I skipped the rest. I mean, I found it interesting when I wrote it down. Now I don't find it interesting anymore. Unless you are really into Ekman-Hilton. Anyway. So here's another example dealing with non-interleaving concurrency. And so we basically touch here on the subject, the main subject of this, one of the main subjects this morning, maybe partial orders. And I also get back to something that Georg showed us in his talk yesterday, when he was talking about comsets. So comsets are a standard model of non-interleaving concurrency. Some people call it true concurrency. And they are basically labeled partial orders. And in fact, isomorphism classes have labeled partial orders. And the arrows that I have here, I mean, I've shown basically Hasse diagrams. But the arrows that you see here, they give us something like a temporal precedence or something like a causal dependency, right? I mean, arrows are patient. You can interpret them in any way you like. And then they are composed during using 2 operations, and also similar to operations that Georg shows. The first one is a serial composition where you put all the elements in the first coset in front of all the before all the elements of the second one. So you need to add lots of arrows to tell that every arrow is before the other up to transitivity that I did not show. And then there's a parallel composition, which is just something like a co-product or a disjunction. And you can see that these operations share the empty concept as the unit. I think this is my only slide about which mentions topology. So there's a notion of subsumption that Georg discussed yesterday too. So if you have 2 concepts, you say that Q substance P, if you have a POMSET morphism from Q to P, I mean like an order-preserving function, as we saw it many times yesterday, this morning, which is a bijection on posets. It means we have precisely the same elements, but we have more order in P than we have in Q. So in computer science parlance, we would say that P is more sequential or less parallel than Q. And you can check that this is partial order in POMSETs. And then, now comes the topology. You can construct an interchange catoid if you take here the Alexandrov topology. So basically, you take the down closure and consider the situation where you have that. And then you can do the standard kind of lifting construction to get an interchange quantale, and in particular, the down-closed languages. So those elements, they form a subquantale of that. So we have now the situation that down-closed languages form our set interchange quantiles. And again, this generalizes to convolution quantiles. This picture here just shows you why the interchange law is actually a subsumption. Right? So you have P sequentially composed with P prime in parallel with Q composed with Q prime. So these blue arrows indicate that the interface is full of arrows from the left side to the right side. And then here you do first the parallel composition and then the sequential composition. And it is as if you stretch the interface between them. And now you also require lots of arrows going, for example, from P to Q prime and from Q to P. Because you need to fill the sequential interface, right? And you have definitely more arrows on the left-hand side, therefore, than on the right-hand side, and therefore it's substitution. So, okay. Why were we interested in these results? Because for a long time, Tony Wall was very interested in concurrent quantales, and he had lots of conjectures of different graphs model for concurrent programs. And he believed that this interchange law is really something like a fundamental law of concurrency. And then we had to check whether it actually satisfied the interchange law, and it was quite troublesome until we discovered, you just need to check 4 axioms, namely those of catoids, instead of 12 axioms or something like that for the quantales. Anyway, yeah, I still have time. How great. Yeah, thank you. Okay, now, I mean, we have basically seen these kind of lifting of the source and target structure of the catoid, and then we have seen an interchange law. And I would actually like to stop here, and then I thought people here would ask, so but what about higher structure? So I would have to answer this question anyway, so I could as well go on and explain. In McLean's book, so he's got this page about single set categories. And then 2 pages later, but only in the second edition, he tells us how to construct single set 2 categories. Right? So you have 2 cells, and then the 1 cells and the 0 cells, they're just degenerate 2 cells, which are characterized as fixed points of the source and target maps that we have. So what he writes there is very nice, and then he says, the identities at the lower dimensions there should, the identities at lower dimensions should be degenerated identity at the higher dimension. And he also says that the 2 structures should convolve with each other. But then here there are many typos and inaccuracies, so I do not want to talk about that. And I just want to go to the next slide and show you how we, and then something else, yes, again from McLean. And then he says, if you know how to formalize single set 2 categories, we can also do n or omega categories, because we just take n categories and then establish basically a 2 structure between each pair, and that's it. So now comes our reconstruction basically of the 2 categories lifted to 2 catoids. So we basically have n catoids that interact via basically the axioms that you saw in McLean's book with minor corrections. And because we have multi-operations here, we capture partiality in a very, very precise way. So which means in particular that the interchange law is an inclusion. It's not an equality, right? It's an inclusion. Interchange laws are inclusions. And then something that is slightly tricky, and it almost killed me when I was alone in Lyon. So one of the homomorphism laws that give you basically the interaction between the structures is an equality. The other one is inclusion. And this homomorphism law is so strong that it's even stronger than a bounded morphism. Okay, but in any case, I mean, following from these laws, you can show that, I mean, you get what you would expect in a 2-category or in an n-category. It's not a simplicial structure, it's not a cubical structure, it's a globular structure. So you can derive basically these kind of globular shapes from the identities that are there in the case of McLean for categories and in the case of dimension.
Can you explain why the inclusion for Struth?
Why?
Where you have an inclusion for Struth?
An inclusion?
Yeah.
Yeah, exactly. I come to that.
Okay.
I was also expecting that you would ask this question, so I prepared a couple of slides just for you. Okay, so first I want to explain why I have an equality, because I mean, to me, this is really the outrageous situation. Why I have such a strong equality. And so in the two case, so the zero composition is the horizontal composition of cells, and the one composition is the vertical composition, right? So and then here on the right-hand side, on the left-hand side, I first do my zero composition, which means that well, I need to meet at this common point, which is basically the target of the first one and the source of the second one. And now if I want to compute what S1 is, well, it has to be basically this thing. If I want to first compute S1 with of x and S1 of x of y, and then do the zero composition, I need to go through the same point. Yeah. So this explains why I have this very, very strong identity. And then, of course, the argument for the target is the same. Okay, now I know that if I fail to explain, Cameron will be able to help me because we did this work really together. So now let's look why this has to be weak. Yeah? So we know we look at the left-hand side here or there, and that's basically what we see in the middle. So we first do the vertical composition now, right? And then we know in the vertical composition, so the sources and the targets, they need to match here and there. Yeah. And then if that is the case, where we know that on the left-hand side, it will also be compatible with what we see on the right-hand side. But then if we go to the right-hand side, we see that we also have situations, because we only require that we can post the sources. So basically these kind of targets that can dangle on the other side here and there. Right? So this means that we have behaviors on the right-hand side that we can't see on the left-hand side. But it's okay, because what does it mean to be a functor in a category? You can only map it if the composition is defined, right? Otherwise it's undefined, which in our case means it's sent to zero. Yeah. And now I think we can also understand the interchange law, right? And so again, you know, we look at the left-hand side, so you see the zero composition, so it must match here. And then we do our one cells after within that, and we compose it like this. And whenever we have that, we can also do it in the other way around. We can first do the zero compositions here, and then the vertical compositions. But on the other hand, when we go on the left-hand side, or on the right-hand side, sorry, so we compose here, I'm left-handed. So we go here and there, so we first do the horizontal compositions, and we have no way of telling that these 2 points actually coincide, right? So we have more behavior on the right-hand side than on the left-hand side. So we have written many, many papers where we said, oh, you know, concurrent linear algebra is somehow special. Because like in category theory, the interchange law is always an identity, but we have a weak interchange law. But no, I mean, that was nonsense. And I discovered it writing this paper with Cameron and other people. All interchange laws, when you represent in this way, are inclusions. That's the way it is. Okay, that's what we see here. And by the way, you know, I mean, I like to play around with interactive theorem provers and stuff like that. So I found basically half of the axioms given on the previous slides are redundant. Right? You only need the interchange law and these 2 strong laws, and all the rest is derived. Right? So that's basically the bare bones that you need. And it's nice to have such a compact formalization, because it streamlines correspondences. Right? You only have to check 3 properties and not, I don't know, 9 or 10 or 13. I do not know. Okay. Now, matching this, we can define what an n quantale is. I do not want to explain the axioms, but it's basically like a matching thing with regard to the axioms that we've seen before. So we basically take modal quantales, we impose the interchange law, and then all these kind of things, all the other identities that would make at the lower level our catoid program. And then when we use this setup, we again get our Eiffel Tower, right? 2 out of 3 properties, and we can justify all the properties that we have on the quantale through properties that basically come from 2 categories, if you think about it. So what's the advantage of that? So with Philippe Malbos and also Eric, Cameron and I, we were working on these kind of Kleene algebras for doing higher dimensional rewriting. So, you know, when I was very young, I proved that using Kleene algebras and modal Kleene algebras, you can prove trivial properties of abstract rewriting, such as the Church-Rosser theorem or the Newman's lemma, which tells you some things about little confluence diagrams. And then the idea was to lift this basically to higher structure, to reason about abstractly and algebraically about facts from higher rewriting, which are basically modeled on 3 n categories or np categories, which means that higher dimensions cells are supposed to be vertical. And then we came up with a bunch of axioms, and it's a main part of Cameron's PhD work, actually. But I don't know. I mean, I always had the feeling that the axioms were kind of ad hoc, right? But through these correspondences, now we can firmly ground them in these n catoids, right? We know basically that the axioms come precisely from 2 categories, and therefore also in particular from the 2 categories are higher dimensional path objects that in higher dimensional rewriting are used for carrying out these proofs, right? And then interesting is, you know, you believe everything is new, but Johnson and Tarski have already shown in the 1950s that every groupoid can be lifted to relational algebra. And in the 1940s, a student of Tarski called McKinsey, he knew that every group could be lifted to relational algebra and also down in the other directions. That in every relational algebra plus some atomicity assumptions, you could actually find a group. So we are really standing in this transition. And I'm not trying to advocate single set categories or anything. I'm agnostic to that. But maybe one of the advantage of the approach might be that when you lift that to higher structure, you have a high combinatorial complexity. In a simple setting, it is maybe easier to model such proofs, even maybe with SMT solvers, which are glorified subsolvers. So that's maybe the idea behind it. Good, I have a conclusion. I do not want to talk about it. Instead, I want to thank people. I mean, there are many people with whom I have worked over the years on this kind of topic on these convolution algebras. And in particular, there were people, you know, with whom I worked very intensely during the pandemic. I mean, half of them are here, basically. And I really would like to thank everybody because they allowed me to stay sane during this very hard time. So I had a purpose, you know, to write a paper or something. Yes, and then also at the end of the slides, you find a bunch of papers. So previously we called catoids LR multisemic groups because they are multisemic groups as people have studied. But then if you go to higher structure, you get these kind of word monsters, which I think in German are acceptable, but in other countries they should maybe be avoided. So now we baptize them catoids. So the paper where I showed the last part is not yet available. It will be on archive, I hope, in a couple of weeks. And the rest, well, you can find at various sources. And that's the end of my talk. Oh, no. Let me say one more thing. What we actually like is to extend these kind of constructions from the globular case, maybe to the pre-cubical case, and then model languages of higher dimensional automata by some modification of catoids, because it has been a long-standing idea of Krzysztof, Uli, and myself to show that languages of HDAs actually form Kleene algebras or quantales or something like that, but we are not yet there. And I think that's now really the end of my talk. Thank you very much.
Thank you, Georg. Thank you for your thinking also. Questions?
Thanks for thanking me.
There's some recurring there. Okay, it's the end of the day and the cocktail is almost ready. So, yeah, please.
There was the first question. So you started by motivating Kleene algebras as axiomatizing language for automata.
Yes.
So are any Kleene algebra axiomatizing some languages for and automata in some sense, or do you expect that?
Well, I mean that would be the thing. I mean that was the original idea that well, n automata, maybe HDAs, right?
Yeah, but that can be called. You can imagine something more general.
We have problems. We have problems with that at the moment. I mean, so this construction that works so nicely for the globular case, we do not know yet how it would work for the Kleene case, for instance, right? I mean that's so to say the grand plan, but we are still far away from it. And again, I mean, Kleene algebras only if you have these kind of finite decomposition properties. So the setting in which everything works smoothly without having to think about, functions being zero almost everywhere or stuff like that is what you get in quantales.
So, if you allow me to comment on this one. So I mean, we've talked about this in your office several times already. The problem I have with this is that higher dimensional automata have all those different kind of compositions of cells in different directions and so on. But for what I consider languages of higher dimensional automata, it's essentially a two-dimensional structure because Georg showed that you have POM sets where you have essentially serial composition and parallel composition, and that's it. There are only two compositions of POM sets, and I don't know how to define any more compositions. Maybe there is something to do, or maybe one should not look at POM sets but at other ones.
No, but this is on the language side. I mean, the automata are really n-dimensional.
Yes,
right?
yes.
But the languages, they become these kind of interval POM sets, which are two-dimensional.
But maybe there is another way to define languages where they also become n-dimensional. Maybe
This
there is something more natural to do. But this is not the purpose of me here. So any other question? Yes.
It's just a question from Radix, I think, that maybe you now have the answer to. Because to my shame, I don't know enough about Johnson Tarski.
Yes.
But does this mean, do these correspondences mean that every n Gaudiya quantale is the subset of some power set of a n category? Or
In this,
catoid?
I would not even make a claim in this generality. I would only say whenever you have a power set,
Then you can
think of me quantile.
so if you have sort
Then-
of a complete atomic
Or
quantale
yes,
something.
or if you have a convolution quantile. I mean, these are the restrictions. I mean, so Johnson and Tarski gave more general statements. So, like Stone's theorem is not only about complete atomic Boolean algebras; it's about Boolean algebras in general. And first of all, we do not know. And then even for the convolution algebra case, I do not know a duality because you have three parameters. So you have somehow to tame a functor or two functors, I do not know precisely. I mean, that's another interesting question, turning these kind of, or finding a duality in this convolution construction. And then, of course, there are two sides to Johnson and Tarski duality. There's the algebraic side, there's the topological side, which then deals with stone spaces and stuff like that. And I have no idea whatsoever what kind of duality it would mean in this concept, and not even where to look. Because I mean, this work with these delta function, it looks different to Johnson and Tarski duality. It looks more like dualities that people know from operator algebras or something like that. I have no idea.
In the sense, the delta functions are the atoms, right?
They are the atoms, yes, but they are completely different. I mean, it's more like in probability theory, where you have point mass functions or something like that.
Yeah, like the
or delta functions in operator algebras. I do not know. I'll prove it in my next slide.
More questions? So I have a question which maybe maybe it's a big question because we tried to do this while you were in Rennes. But you know, on Friday, on Thursday, there will be a whole day about weak higher categorical structures.
Yes.
Right? I mean, I know the answer. Currently, we cannot do a weak or lax
Yes,
categories in this set.
Yeah, exactly. No, I mean, so again, I mean, it's a very interesting comment, and that's also something we are working on because here we are basically in the strict setting, so we cannot do bicategories. So we know how we can do natural transformations in the single set setting, basically copying and translating from Freud's book. But then, you know, to really weaken the setting so that you have, you know, like associators, relators, unitors, or something like that. We do not know at the moment how to do that in the single set setting. Right? That's another interesting question. If you could do that, we have bicategories. With bicategories, we would also be gain flexibility that we probably need in order to prove these statements about languages of higher dimensional automata. So that would be one of the building blocks.
So an essential stepping stone.
Yeah.
Right. So I don't know if people have been doing single set higher categories.
Nobody has ever done a single set since the 1990s.
Okay. Any further questions? Okay. So then let's thank Georg again. And I believe